This is chapter two, or part two, rather, of covering chapter 11. And we are going to be talking about the interior of Earth. So we'll talk about the structure of the Earth and its composition. So the structure of the Earth, its layers. Um, how do we know that those layers are there? We've never sampled very deep. We don't know what's down in the center of the into the center of the Earth, right? Nobody's been there. We can't. And drilling, like digging, the deepest hole that anyone's ever drilled only goes about 2 to 4 kilometers into the crust, and the Earth is it's more than 6,000 kilometers going from the crust to the core. So how do we know, or how do we think we know? We use seismic data, and that's a whole topic all by itself. But the idea is that after an earthquake, seismic waves move differently in different layers depending on how dense the layers are. And we've also modeled the layers of the Earth using tomography, seismic tomography. So again, it's something that we get from the speed of the seismic waves, but in this case, it has to do with the temperature. Different layers are different temperatures. And so, in any case, we do have this data that we have been able to model the interior of the Earth. The three layers that are listed over here. We're going to start with the core, go to the mantle, and then the very outer part of Earth is the crust. So here's a depiction of these three layers. Um, the core, the core is the innermost layer, the mantle, the crust, and the outside. But we see that the core has been split into an outer layer. Just circle that here, the outer layer, and the inner core here, right in the middle. We split them into inner and outer core because one is liquid, an actual liquid, and the other is solid. Altogether, it is iron, mostly iron, with a little bit of nickel. Um, so the only difference here is whether it's a liquid or solid. And I'll explain why we have a liquid layer here, um, when we would think, oh, but the center of the Earth is the hottest, right? And it is. Um, so why wouldn't this be liquid also? Um, it is solid because it's the pressure. The pressures are so great that um, the pressure is actually squeezing the atoms together. And when you do that, when you squeeze the atoms tight enough together, the material has no choice but to be a solid. Those are the kinds of pressures we're talking about. So in any case, that's why the very interior of the Earth, the very most inner layer, that is solid. But this is a good thing that we have solid and liquid metal, um, because as the liquid rotates and moves around, and the inner core rotates as well, and so both of those rotating in different directions at the same time, that rotation produces a magnetic field. And just a really brief on the magnetic field. What it is invisible. It's not anything that we can see. We can measure it, but it's not visible. We have a north and a south pole. And so that looks like a bar magnet, right? You have a long rectangular bar magnet, and there's a north pole and a south pole, and that's pretty much what ours is as well. It looks a little bit like this in the box on the bottom left. That's we don't have a literal bar magnet inside the Earth, but that's what one could look like, just to jog your memory. What we do have, though, not the bar magnet in the Earth, but we have the magnetic field that looks just like a bar magnet's magnetic field, where the field lines they wrap around the Earth and they're coming in or out at the poles. So that's just a little bit more about the Earth's magnetic field because of the rotating solid and liquids. When I said it's invisible, it is. However, certain times of the year, we can see um, what we call the aurora borealis. However, what a lot of people don't know is that there is also an aurora australis around the South Pole. Australis refers to south. It's kind of why Australia is called what it is, because it is south. But yeah, not too many people see that um, the around the South Pole, and I usually ask the class why they think that is. Um, and I'll give you a second to think if you want. Right? Why do not a lot of people see or talk about the Aurora Australis? It's mainly because nobody lives uh, around the south part of the Earth. It's mostly um, it's what is it? Oh, Antarctica, uh, where very few people live or spend any time. The very south part of South America, um, and that's about it. So yeah, very few people have seen it, so not there's not a lot of chatter about it. In any case, they appear when there's a flare and increase in solar radiation. So, yeah, a sun flare produces more radiation. And when that encounters with the magnetic field, which is charged particles, it emits light. That interaction between the radiation and magnetic field lines, it emits light, and we can see it. And that's why they look so kind of stretched out and long and just arcing up into the sky. They're following the magnetic field lines. In any case, thought that's an interesting um, fact about the core, the magnetic field, and all that. One thing that I like to talk just a little bit about is the fact that the magnetic poles they move. So over here in the on the map, I'm going to explain what I mean by that. On the map here, the geographic North Pole, that's the point or the axis about which the Earth rotates. And so that does not move. But the magnetic North Pole, it does. And it moves because of probably some complicated fluid dynamics that we try to model, but it's very complicated. So um, we don't know why exactly. We can't predict where it's going to move, but um, it does move. So another interesting thing about the magnetic field is that not only does it move its location, but we also have been seeing the movement increasing. It's speeding up how much it's moving, how fast it's going. And it's been doing that since about the 1990s, 1995, I think. Um, the rate at which it moves was speeding up to a point that we had to redraw maps on a faster basis. And what I mean, the reason we have to redraw maps at all is because the magnetic field, the magnetic poles do move. And since navigation uses the north magnetic pole uh, for its navigation with compasses and things like that, um, they if the magnetic pole has shifted and they don't adjust for it, they will end up not going where they wanted to go, to put it that way. So that these compasses are set correctly, people are going where they mean to go. Um, we do periodically have to redraw maps. But again, in about 1994, as it was moving faster, we had to be redrawing maps instead of every 5 years, every three. We had to do it on a more regular basis. And so that can be demonstrated by the fact that this uh, distance was covered over about 90 years, whereas about the same distance was covered in just 20 years. And so it was kind of a big deal. Um, and so I actually, since that stopped in 2015, I updated it 2019, 2023. It the magnetic field is now slowing down a little bit, and the models predict it to be moving slower into 2030. That's how far they've predicted things. So I even just looked up where 2025, where it is today, and it's pretty marginal how far it's moved in 2 years, which seems to back up the idea that things are starting to move slower again. Um, all this to say that we have our the Earth's magnetic North Pole here near the North Pole, the geographic North Pole. But in Earth's history, that hasn't always been the case. There have been times where the magnetic North Pole has flipped and is then near the geographic South Pole, and vice versa, where the South magnetic pole was um, near the South Pole, it flipped to be up near the geographic North Pole, right? So, like the North magnetic pole goes to the south, and the South magnetic pole comes to the north. That has happened, that we have evidence of, hundreds, if not thousands of times. I'm leaning towards more the thousands times. Um, and that we do have data. We have plotted it over time, since this is something that has happened over very, very long periods of time. So that's what these black and white bars are. Hopefully you can see those. I'm dragging the cursor down one of them, and then there's a second one here. We're going further and further back in time. The beginning of the Mesozoic, about 250 million years ago, down here, to today, which is up here. So these black bars, they represent what we call normal polarity which is what we have today, the North Pole at the North Pole. The white bars are when the Earth's magnetic field is reversed. North is at south, and south is at north. And so every time you see a black switch to a white bar, switch to a black bar, we are seeing magnetic reversals. And we can zoom in here. We can see that we're in a time where we have normal polarity. And then we can see all the times that the black and white bars have flipped. If you see gray, that means the reversals were happening very fast. So they're not they can't be discerned at a scale like this. In any case, one thing that um, I see in the science news every now and then, I see a headline that says, Earth is overdue for a magnetic reversal, make it all sensational, even though there's no evidence that a magnetic reversal has done anything to the Earth. Definitely no mass extinctions, which people often um, bring that up as, humans could go extinct with a reversal. It's also a dumb thing to say because a magnetic reversal, as best we know from experiments we've done in labs, these reversals take place over the course of 100,000 years. So it's not likely to impact um, Earth at all, or humans at all. Well, also Earth. Um, I was going to say something. Oh, the other thing is the way that we think the reversals happen is not that the North and the South poles slowly move around the Earth. Like at one point they would be around the equator. We don't think that happens at all because we have no evidence of the poles being near the equator. Um, so what we think instead happens, which the models back up, is that the magnetic field gets weaker and weaker and weaker and weaker, probably just due to the different flow dynamics in the core. So as it gets weaker and weaker, it can then flip. Again, not move slowly from one pole to the other, but it just instantaneously flips while it's weak. Makes it easier for it to flip. Um, and then it strengthens again, and we get a stronger magnetic field. We think that takes about 100,000 years. So you're not too well. Sorry, yeah, 100,000 years. We're not going to notice. Hasn't done anything in the past. Um, okay, so I don't like the headlines that say that in any way, but the other problem is saying that we're overdue because that means that a reversal happens periodically and cyclically. Um, which and so um, if something was happening at a periodic interval, you would be able to predict the next one. And if it didn't happen, yes, you could say it was overdue to occur. But do you see a periodic or cyclic pattern? You see any pattern at all to these reversals for the last 20 million years? Do we see any pattern to that? Or regularity? That's another way to put it. Hopefully, we're all saying no. It looks random. Um, so there's really, I'm gonna point to over here with this really, really long black bar. in the Cretaceous. That's about, I always like 50 million years or something, where there was, as far as we can tell, we have tested and tested rocks, but as far as we can tell, there was no reversal during those millions and millions of years. But then there's periods like we saw here in the Jurassic or here these gray bars where the magnetic field was reversing very fast. Again, as best we can tell. So because of that variation, no pattern, no regularity, you can't say that something is overdue. We could be starting another superchron over here. That's what we actually call that. We could be just at the beginning of that, and there's tens of millions of years left. Who knows? So I hate headlights like that. And I just thought I'd say that if you see someone say that, it's crap. It's not true. Okay, so that was the core. Moving outward toward the center of the Earth, the outside of the Earth is the mantle. And I'm not going to talk too much about. I'm not going to talk about the different layers of the mantle, but it is very, very thick. It is 82% of Earth's volume. We do have convection, um, mostly below a certain depth. And it's that convection mixes. It helps mix the mantle. There are places where um, anomalously hot mantle is going to move um, upward. The colder parts of the mantle will sink. And so you have that convection that occurs. Onward to the crust. I didn't have a lot to say about the mantle. Onto the crust. We have, no, let me start over. The crust is the most outer layer of the Earth. It's the thinnest. Uh, the thickness of the crust varies from 35 to 40 kilometers in what's called continental crust. Continental crust is where the land is, um, makes up the area above water. That's continental crust, making up the continents. The oceanic crust, on the other hand, is thinner, even thinner than the continental crust. Its average thickness is just 7 to 12 kilometers. Not very thick at all compared to Earth's, what was it, 6,000 and something kilometers. So very thin and very dense compared to continental crust. Um, it is that density is because of what the oceanic crust is made of, which is mafic rocks, and that's a word that you're going to want to remember. Mafic. It will come up again in the next several chapters. Um, that term, well, we'll talk about that in a minute. The continental crust, on the other hand, less dense and is what we call felsic. It's made up of felsic rock like granite. So this is our outer layer, oceanic crust and continental crust. It is separated from the mantle by a layer called the moho. That stands for the Mohorovičić discontinuity. I don't know if I say that correctly, but I've tried. In any case, that is the boundary between the crust, not just continental crust, but oceanic crust as well. And so, yeah, this is the moho, and it dips down or comes up a little bit further. It is dependent on density. The mantle rocks are denser, continental crust or any of the crust is less dense than the mantle. There's another way of looking at um, the very upper layer of Earth. Um, we call that the this layer, this particular layer, we call it the lithosphere, and below the lithosphere is the asthenosphere. Now let me explain a little bit. This layering is not dependent on density, right? Where all the crust is less dense than all the mantle. This distinction is made based on rock strength or rigidity, I guess we could say. So the very outer layer of Earth, the crust, and part of the upper mantle, the upper layer of the mantle, part of that too. These layers are cool enough. The temperature hasn't increased as much uh, in this rock, and so it behaves brittly. The crust and the upper mantle, they kind of stick together because the temperatures haven't increased that much, and they're stuck. And this lithosphere is uh, is what makes up tectonic plates. It's a rigid uh, piece of layer of rock, um, and it is sitting on top of the asthenosphere. And the asthenosphere is still the mantle. We call it the asthenic spheric mantle. Um, but the asthenosphere can move as a soft solid. So the brittle layer, the lithosphere, sitting on top of the asthenosphere. The lithosphere will move around, crust and upper mantle. But the asthenic spheric mantle, the asthenosphere flows more. And what we'll get into later is the spots where the asthenosphere is flowing up. This usually marks the edge of a plate and where another plate meets them. But we'll get more into that later. Um, okay, yeah, I circled some of those. Lithosphere and asthenosphere are two other ways of talking about the outer parts of the Earth. So I have a quiz question for us, a review question. Remember, you can always pause if you want to be able to think about it for longer. The geologic time scale uses equal intervals in dividing the Earth's history into eons, eras, periods, and epochs. Is that true or false? Okay, that would be false. The intervals are not equal. That's maybe that was tricky because of that. We do divide the Earth's history into eons, eras, periods, and epochs, but the key here was, are they equal intervals? No, they can be all sorts of different lengths of time. Another one here. The lithosphere is made of the outer core and lower mantle, asthenosphere and lower mantle, crust and upper mantle, crust and inner core, core and lower mantle. We have C, crust and upper mantle. All right. Yes, last one here. The boundary between the crust and the mantle is known as the A, moho, B, asthenosphere, C, Gutenberg discontinuity, D, ductal mantle, and E, none of the above. And our answer here is A, the moho, or the Mohorovičić discontinuity. Not the Gutenberg discontinuity. That would be easy to pronounce. It's the Mohorovičić discontinuity. All right. So uh, that'll be the end of the parts, or this part where we looked at Earth's layers, compositional and structural. The next unit will be uh, talking about the geologic cycle, um, and the rock cycle, the hydrologic cycle, and the tectonic cycle. So that'll be next, the next part.